All right, good morning, everybody. Now it's 11 o'clock at Denver, Colorado, and welcome to the Spring 2025 Computer Vision course at the University of Colorado Boulder. And my name is Tom Ye, and I'll be your instructor today. And today's lecture is a special lecture I have been preparing, and it's going to be on DeepSeek. And so I was reading the news last week. There's a lot of people talking about it. I decided to make it a public lecture given the high level of interest. But over the past 2 days, the interest has gone up even higher than I expected. But anyway, so some of you might be in watching this on YouTube live stream as well, because our webinar doesn't have the capacity to accommodate everybody. So some of you might be redirected to the YouTube live stream. And today I am glad that I have assistance from Anna, who is my TA for this course for several semesters, and she will be fielding questions at the Q&A feature while I'm focusing on the lecture itself. And I have two other students, Milton and Nolan. They will be monitoring the live chat on YouTube, so you can ask questions there as well. And if I have time at the end, I will pick some questions has not been addressed, but they were committed to answering all of your questions afterward. And we'll go through all the questions and provide answers to your questions. So feel free to ask questions along the way. And today, my focus is going to be on the inner working of DeepSeek, on the more like inside the black box. There's plenty of commentary out there about how what it can do and what kind of benchmark result is being able to achieve. So although I have my opinions, but I will not answer questions today about, well, like stock market prediction or how closer we are to AGI and so on. All right, so I'm going to focus on this spreadsheet right in front of you. And my goal is that by the end of today's lecture, you will be able to feel comfortable going through this yourself and being able to even implement all the different components we're going to see today and have a pretty solid foundation of knowledge of how transformer works and also some of the new innovation that introduced by DeepSeek and such as multi-head latent attention and also the mixture of expert the algorithm, and you have a bit better understanding of that. All right. So before I start, I would like to encourage you to go to this website by-hand.ai/GitHub, because a lot of people ask for not GitHub, and you'll be able to find link to this very document. I already sent this out to many of you, but if you have not been checking your emails, you might have not received this. So I usually encourage my students to have a copy of this on their local computer, so you could follow along if you want to. You can also sit back and watch. I decided to share the recording. It might take us a while to edit it, so you have bear with us while we are editing the recording, but we'll eventually share it. And you'll be able to follow this and review some of the content and try to replicate what I'm going to show you today. So anyway, so this is the quick overview of what I plan to do and what I wish I can accomplish. I just delete this. So for now, I'm going to focus on this. All right. So first, I would like to provide a roadmap of what we'd like to achieve today. And so this is the model, simplified DeepSeek I developed for the purpose of understanding how the algorithm work, also be able to teach in my class. And so today I'm going to take you from input and on top up here and going down to talk about one of the head in the attention mechanism. And I'm going to show you how we add another head. It becomes a multi-head attention mechanism, and how to add another head. Now I have three heads, how we could concatenate the output from these three heads into one place, and how we will run the output projection step in order to bring each hidden token back into the same dimension. And then we'll feed that into the feed-forward network layer. And we're initially going to look at just one expert, and one before a network, as in the original transformer architecture. I'm gonna show you what happened. We have another expert. What happened? We have a third expert, and so on, fourth expert. How we can mix them together and produce our final output of this model, and go back to talk about the router. How would routers uh, be used to decide which expert to use for a particular given input? Okay, so this is like overall roadmap that I'd like to go through. It's pretty ambitious, but I would like to build this live in front of you. Hope you could follow this as we go, and I'll make my commentary as I go, as I am teaching in my own class. That's how it's going to happen, how things gonna work. All right. So let's start with input. We're gonna zoom into 100% all the way to the top. So input to the model, like the DeepSeek, is based on transformer architecture, is that you will have a series of tokens where each token corresponds to a word in the sentence. There's some process called embedding that return a word into a token. So today we're not gonna go too deep on that process, but we'll just like to take the input as a given. It's going to be so let me use this word. What I like to do is I would use this color to just to remind me that input, I have this input 1, 2, 3, 4, 5. I have 5 tokens. I just like to draw this as an exercise to remind me that if I use this representation, my input is actually a column vector. I have 6 of them. Each one, I have 5 numbers. 6 token, each token is 5 number. And you might heard of the word called model size. When you're trying to implement deep learning model, transformer model, you can pick the model size or hidden dimension size. In this case, the model size here is 5. And the term context length here is actually 6. They're very simple examples. And okay, it's actually, I think okay, here, now you can see it a bit more clearly. Is that right? Okay, 5 and 6. Okay, and then so I'm going to bring all the way down to the first head. But before I do that, I would like to just hide this part a little bit. This is a positional encoding and also the latent. There's a bit more advanced stuff we're gonna talk about. But before I do that, I'm just gonna hide all this. How can I hide all this? Okay, I'll select all this section from row 12 to here. I'm going to hide this. All right. So if I hide this, you can see in this more clear. We have an input. We're trying to feed it into the first attention head. But I would like to start with the value vector. You might heard of this query key value in the particular attention mechanism. So I was focused on value first. Now you're gonna know what I meant when I try to do that. So I'm gonna use this color again, maybe use this color. Okay, so there are some mechanisms that we could convert a 5 value into a shorter vector. In this case, I can have 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I'm just for 1, 2, 3, 4. I'm gonna come back to talk about what's going on here. How does the transformation work? But I want to just to show you that if there's some process that we would like to go from a higher dimension 5 to a lower dimension in this case, the per head dimension is what we care about is 4, going from 5 to 4. Give you a like real world perspective in the paper of this DeepSeek model. So the model size is like 7,168. So and it's much bigger than 5, but then in my illustration I just use 5, but the example generalized to 7,168, and 4 in the actual paper is 128. So going down from 7,168, and we select 128 of them in some kind of combination, so much lower dimension compared to the input 7,168. But in this case, 5 to 4. So, and then afterward, I like to bring this to the attention part, and this is just a reference, the same, exactly the same value. But now I would like to spend a little bit getting deeper into the intuition of the attention mechanism, how the math works. So suppose we have some number in this case. I'm going to use some real number to show you how this works. Suppose I just consider, okay, let's fill this up. Say we have 1, 2, 3, 4. There are 4 numbers here. Okay, and I also have just another one, 5, 4. So let's say no, just say 5, 6, 7, 8. So suppose somehow this I we so these two tokens, 3 and 4, and then we retracted some values, 1, 2, 3, 4, 5, 6, 7, 8. Let's see how this attention mechanism work. Is that, well, if we have this attention weight here, I'm just write down some attention weight here and explain how they work. So suppose we have a 0, 0. Let me just use the last position. Suppose 0, 0, 1, 1, 0, 0. What does it really mean? What it means is that, so if we consider this one, it's kind of map over here. This one map over here, it sort of tells us that which one of these 6 tokens I should pay attention to. In this case, is 3 and 4. And since they're all 1, 1, then we can calculate this. Basically just add these two together. 6, 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10. So this is what we have, okay? 6, 8, 10, 12. That's what this number means. Suppose I use a different color and to do another column. This case, I would like this to be 0.5, 0.5. There's another set of attention weight, but in this case, this sum to 1. In fact, this is what softmax is going to give us. We apply the softmax later. You can see how it works. But what the goal is that we'd like this entire column to be some kind of distribution that add up to 1. So in this case, let's modify this a little bit. It's going to be take half of the 1 and half of 5 and add them together. And the end result is half of 6. So this is going to be 3, and this is going to be 4, this is going to be 5, this is going to be 6. So anyway, just give you a sense that, well, in this attention mismatch, our goal is that we'd like to form a new token over here by combining some subset of this token with the various weight, which are specified by this weight matrix. Suppose I give you another one, like 1, 0, 0, 0, 0, 0. What does it mean? What is it? I hope you know how to interpret this attention weight vector column here. It means that I'm paying attention to just the first one. Nothing else. Everybody else is 0. What if we have something like 0, 2, 0, 2, 0, 2, 0, 2, 0, 2, and then that's 1, 0? It means that I'm paying attention to 1, 2, 3, 4, 5, which is 1, 2, 3, 4, 5 here, equally 20% each over 5 of them, but nothing to the end. Hopefully, this is what it can give you an idea what it is. But I'm going to want to show that exactly how I implement it. Suppose I'm going to use a real number, 1, 2, 3, 4, 5, 6, 7, 8. I'd like to show you that if I put 0, 0, 1, 1, 0, 0 over here, in order to reproduce the calculation I have for the last position, 6, 8, 10, 12, all I have to do is to do a matrix multiplication, which is, maybe just put some random number here, 0, 0. So okay, ignore this. Okay, so I have a full value, but I'm going to implement matrix multiplication, mmult, which is the built-in matrix multiplication function in Excel. And all I have to do is select all this. And then I go up and select just first row, because our first column, I only pay attention to the first column right now. All right. Okay, did you see? Okay, it's embarrassing. It didn't quite work. I want to see 6, 8, 10, 12 here. But for some reason, it's not giving me the number. Okay. Oh, I see. So it's now 1, 1. I make a mistake. So this actually third, fourth position is 1, 1. So I want to do is first and second position, they will give 11, 14. Actually, this is first 1, 1. This is what I want. 1, 1, 0, 0, 0, 0. Give me 6, 8, 10, 12 because it selected the first and second position and combine them by 1. So if I change this to 0.5 and 0.5, you can see that the weight just gonna change to 3, 4, 5, 6, kind of match things to my right. Anyway, it's pretty messy here, but I think it's important to kind of go through this fundamental math. You feel like you can just add this up together on your own, right? So this is how the attention mechanism works. But for the rest of the attention mechanism, I might not go into this math at this level, but I want you to appreciate this so much that I'm going to use a pretty rainbow color to sort of visualize that process. So suppose I have this is what I want to derive. And it comes from this attention weight here and this attention weight here. Kind of pretty, right? It's almost another thing to think about is that in order to derive this new token, I'm going to pop this up to the top, following the rainbow, and pop another one because we have two attention weight over here, and drop down a new token. That's combination of the two. So you're gonna just for you to remember this pattern, I'm gonna erase everything else just because it's distracting. But I'm going to just leave this rainbow over here to to appreciate this. Okay, because just I have so later on when we go down to the mixture of expert layer, when we talk about fast forward and feed forward network, you're gonna see this rainbow again, but in the opposite direction, in the other 90-degree, kind of in a different orientation. And then you study to understand why we need a attention layer and feed forward layer. Each one combines your features in a different orientation. We're gonna become clear once I got to that part. All right. So let's come back here to the values, tracing back to this value. Where does value come from? So value want to come from this input. So right now I'm gonna just drop some input in. I just kind of type some random number in, and type a lot of 0 first, and then this is I'm just randomly generate some input as an example. Okay, so I don't even know whether it will work, but just gonna type some random number as I go. No, I don't want 8. 8 too big. Okay, maybe here. So this is the input. So I'll have this 5 by 6 matrix. I like it to become drop down to 5 dimensions. Drop down from 5 dimension to 4 dimension. But the other direction, the context length is still the 6, not change, not so to do that, all you have to do is to actually apply a matrix of the particular form. If I lay this way, it's very easy for you to determine the size of this matrix is 4. Okay, and this is going to be, this is my visual cue for me to know that I need 4 of this in order to match each dimension. So this is my particular favorite way to represent matrix multiplication. So we'll multiply 4 by 5 matrix with this input. We're gonna get a new set of vectors over here. So that's how the linear projection work. So to show that, I'm going to also type in bunch of random weight. But I found, okay, let's start with initially it was 1, but just drop some 1 in some random location. And sometimes maybe I add another -1 here. Okay, so this is just kind of weight. So once I have this, I could simply do a matrix multiplication and select this weight. And then, okay, and I go up to select my input here. And then I get these values. Projecting from input vectors or hidden vectors to a value vector through a matrix multiplication. And then I will come down to copy this. I'm going to delete these values over that's there. But in Excel, I could do is that I can just say equal sign, come back here to select all this. So this is an array operation. I could just set this array there, make a reference to the same array. And now all I have to do is figure out a way to calculate this attention matrix, and then I can do a matrix multiplication to get the attention weighted value, which is the output for my attention head, for first attention head. So going back here, we need some sort of things that, well, this is a distribution I want. After softmax, I'll get the distribution to add up to 1. But this is a raw score. Sometimes we call this an affinity score. Some kind of score can indicate that I have high score, meaning that I want to pay more attention to the position. Low score, meaning I don't want to pay as much. How do we calculate this? So that will require us to compare a bunch of keys and also a bunch of queries. So I'm going to use this to this color, maybe this color. So I'd like to have some kind of well, maybe use this too pretty. Use pencil to draw 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So that's 6 different query vectors. And use a different color to maybe draw also 6 key vectors. And when we're trying to compare them, I would like to compare every single key to every single query. And so if I visualize this, I have this, I could do a matrix. So there's 6 of them. And then I use my key again. This is kind of visualize the thought process of understanding this. I want to compare my key, I mean query, this is query here, Q, to first key, second key, third key, fourth key, fifth key, and sixth key. And do that again, do that again. I just kind of internalize this process and realize that you have 6 by 6 intersection, meaning a comparison between a particular pair of key and query. So each intersection is a dot product in the linear algebra. So that's what we want to accomplish. So now, where do we get this query? So we follow a similar process that we could project down from our input vectors to get a shorter vector of 4, going from 5 to 4. In practice, it's 7, 168 to 128. Okay, so let's do the same thing for the key. We have this one. So my goal is to have something like this. The key will come over here, and then we'll have some quick query can come back over here. And then we take the dot product between every single pair of key and query. Then we get this and run softmax on it, and we can get our attention matrix. So that's the goal. So we can repeat this linear transformation. So I could copy my weight here just for convenience. I copy this way and move out to the top and copy this again so that they are same shape. But I can just change a little bit, just say that the way it's going to be different. The learning algorithm is going to keep learning to how to update this way in order to satisfy or improve your learning objective function, reduce your cost function, and so on. Okay, now I have a different set of way. I just manually change them. Following the same equation, I'm going to say equals mad mod and go down or go over here. Okay, and going out to select my second matrix. So what this matrix modification does is going to just linear project my input vector into a query vectors. So repeat the same. Okay, and then I could go up to select my input vector. So you might realize that they are using the input vector 3 times. And if you check the math, if you interesting equation is kind of like you see this form. You say input is U for hidden value, or maybe H. Just use H. H is a hidden value, kind of hidden vector. So this is going to be WH and become your query vector. And H, this W key H to get your key vector and so on. You see that in the equation. Now we're going to move over here so we can try to do a dot product between them. So I'm going to copy or actually refer that, make a reference to this array. And this one, I want to make a reference to the key array, but except that you might notice the orientation actually different. We need to transpose this. So we can fix just those transpose and going over there to select my key vectors, and then voila. So we have all the key vector and it's kind of ugly. So just remove this. Can I just see that now clearly? So once I have this 2 thing, and then we can do that matrix modification between the 2. So okay, so now I'm ready to perform matrix modification. So the first one, these are all the keys, transpose of the keys, and these are all the queries. And then when we have this, we'll have a 6 by 6 matrix of affinity score. All right, it's kind of ugly. And then so in the paper, you'll notice that I have a little normalization term here, which I'm gonna skip. This doesn't really you don't yeah I will skip it for simplicity reason, but I want to focus on the softmax. So you can see all these kind of value over here. It's quite large. I like to map this into some kind of probability values. So the way we can do it is that I can just use a softmax. I should build this function myself. I won't go into detail today how softmax great, but what you need to know just that it's going to be speed. Okay, it's pretty small, right? I could come back here. Okay, so let's just hide the ink a little bit. You can see that So in this case, we one, come on, hi. All right. So you can see that 63 and 65, they are like the largest two numbers, and they are mapped to the probability of 0 0.1, 0 0.9. Doesn't let me hiding. Okay. Hi, stay. Okay. And so I come back again. Anyway, so in this case, you notice that every softmax is going to be applied to the column. So I can copy this over again, over. So now this is my attention matrix. Notice that every single column, A dot to 1. Now I'm ready to multiply my value matrix to with my attention matrix. And this is my one final step to complete my first attention head. I'm kind of excited about this. Finally. So this is my final step to accomplish this attention head. So this becomes attention weighted matrix. Following the rainbow, note, remember, and get a new token following this attention weights at this matrix in softmax over here. And then end of the attention head. And now I'm gonna bring you down here to see where this goes. Kind of scroll out one a little bit. So one is that I would like this to go all the way here to take on the first spot of my concatenation. Because right now only one head. So I'm gonna make a reference equal sign. I kind of go all the way, travel all the way back down here to bring this down. Okay, and now I have this one. All right. Now this is the last step. Before we can pass on to the next layer, we have some business we have to do. So I'm going to zoom in to show you the last layer of output projection. Why is output projection is needed? I chose all this dimension all with intention to with intention. So well, remember this is head dimension is 4, but for the model size, we've actually picked 5. And that it doesn't quite match. 4 is not 5, but it needs to be 5 in order to be compatible with all the other layers. And one thing about the transformer is that every single layer has take exactly the same length, so you could actually have this interchangeable module. So how do we go from 4 to 5 again? So we need a 5 by 4 matrix over here. So that's what we need here. So if we can somehow put a bunch of numbers here and multiply them, so we'll be able to do that. Let's put some 0 here, but put some 1 here, 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. Okay, so once I have these weights, so I can show you how we can then do the final projection. This is still a single head case. So final projection to this guy. Okay, and then we can have this output. Should we shape that into what I want? So in practice, it's 128 to back to 517 something. Okay, but in our case, is 4 to 5. Okay, but I have saved some space for the second head and third head. You can see that as we have more head, this 4 is gonna grow into 8, grow into 12. As we do that, we also have to grow our weight matrices here to 8 and 12 similarly. We can see how it goes. So that's my next step. Next step is to show how we can then take this and just implement our second head and third head and so on. In fact, it's actually quite easy. All I have to do is just copy and paste all the calculation I just had, but with some caveat. So one is that I want to copy all this section down to the bottom. And with Excel, everything's relative, so I can copy most of the formulas still kind of work. The only thing that won't work is that I have this referencing the input. Do you see like V5AA9 referring to the input? So all I have to do is if I could fix the row number, I'll be able to copy all this down there without changing the equation at all. So let me just show you. I'm gonna fix 5 and 9 because in Excel, this from row 5 to row 9. I want to use for them to use the same output. And when I'm doing this, okay, you'll see why that could work. Okay, now all I have to do is I just going to do copy all this. Okay, copy. Is it about right? Okay, copy. All right, and then I'm select the first position to make sure I select the right location. I'm gonna copy all the formulas and values. Voila. So it just work, okay? It match. But it still get the same result because I copy the same set of weight, but we could just change the different set of weight just to make a point that this is actually a different head. I just change a few weights to make them different. So I don't get the same thing. Okay, so this is my second head. I just do the copying. And then as a review, so we have softmax here. This is our key and query dot product or maximum application. And then we can get this all add up to one sort of, and this is my final attention weight values out of my second head. And then I zoom out a little bit. So I would like to do is then bring this to down here to my second output as well. I mean, second output, so I'm going to select here and equal, come back up here. All right, and select here. Can see that what I'm just have accomplished with this is that I concatenate the output of the first and the second head into a longer column vector sort of matrix here. You can actually visualize it. Now I could do the copying one more time for my third head. And if you have 128 heads, you just do it 128 times in your implementation. So I'm gonna copy this again and move down here, copy, paste formulas, and voila, I get my third head implement as well. And then I'm going to just do the select here and select this, bring out my third head output. And so now this is almost done with my multi-head implementation. Now I zoom in because I do want to make sure my third head is different. Now my third head and second head are identical because I just copy all the weights, but I'm going to just set some zero to make a point that these are different head doing different things. 1, 1, 1, 0, 0, 0, 0. Okay. And now as I'm doing that, all the calculation kind of changes. I also bring this to my third section. And now you can see that all the attention weighted feature after you concatenate them is 12. I purposely pick them so that they won't be 5. You still have to down project this into back to 5 in order to feed to the next layer. And the way to do that is that through metric multiplication, now we need more weight. So I just copy the weight, there'll be more weights, copy more weights, and change a few things. So these are different weights. So not exactly identical. Otherwise, it's a very boring example. Okay, so now I have to do that. And now I go back to update my equation. So you can see that initially with only one head, this is the highlighted area are the maximum applications they are involved. But now I have a more head, 2 and 3 head. All I have to do is to just become the larger metric multiplication. So if more, you have to load into the GPU to multiply matrices, except that you can see that the output is still exactly the same. It does not change as you scale out the head. In this case, you can visualize that it still gives you the 5 because you have this output projection to bring back to 5. All right. So this is, I think I'm good on time because I do want to spend half an hour on multi-head attention, which I just managed to accomplish. All right. So let's go back out a little bit. So now let's review. We have model size 5, and we have context length 6. Can you just see this number? And then we also have number of heads. Now in our example is 3, but in the paper is 128. So you times these two numbers together, it's quite large. What is this number? Some kind of large number. What is 128 times 128? I can't be sick right now, but it's a large number. And so this number, 108 times 128 is a 12 in our case. So in fact, so this is in the real model, it's going to be 128 times 128. It's pretty big. then you have a really large output projection matrix to help bring it down to your output, which is by 5172, something like this. Okay, so this is how dimensional changes. Okay, now finally, I get to talk about DeepSeek. So what does DeepSeek bring to the table here? So going now, we want to go from multi-head attention to this new thing, which is this new keyword. Did you see? Which is the new keyword, the latent. What does this latent really mean? All right. So now I bring back to these things I've been hidden for now. So I'm gonna unhide this. So latent is an idea of basically to reduce dimensionality to be something much smaller, but you don't really see them. They're hidden. In the case they are hidden from your input, even though input is called hidden, but you hidden from the hidden. It's kind of the recursive there. But anyway, so another purpose is that you can compress the dimensions. In the paper, you use the word compression. And in this case, when you pick compression dimension, let's say, in my case, I want to compress from 5 to 3 for my query. And key value is another compression I like to do, but I can do it together. So from 5 to 2. Then when I decided that's my compression, so all I have to do, what do I have to do? Another metric multiplication. You can see how many metric multiplication we've been looking at so far. They explain, give you some idea why GPU is important, why NVIDIA is actually valuable, and why DeepSeek shows that we actually do not, you can use much fewer metric multiplication to achieve the same result, and NVIDIA stock was in trouble. Anyway, putting that aside, so I'm going to quickly build this projection matrix by putting lots of ones. I'm 0 and ones. 1, 1, 1, 1, 1, 1, 1. They put another -1 just for fun. Okay, I'm putting some -1 here, and then we could project that into between 5 to 3, and do the same thing for the second half of this. 1, -1, 0 and 0, and matrix multiplication. One more time, matrix multiplication, and first matrix, this weights, second matrix, this input vectors. All right, so now I have just compressed this in the equation. In the paper, you will see that they just have this similar like a W dq times H and get this C on the C, T, and Q, and T basically all the token positions, 6 of them. So I have 6 of them. So there's compression. But then for now, you may be wondering why I'm doing this. What is the benefit of doing this? The benefit become clear when you're trying to update the way that you run attention, multi-head attention. Maybe it's a good opportunity to actually take a stop, because now I gotta make some major change. They just make a copy so I can save this, so that you can compare the difference. So this is, I just make a checkpoint here. All right, so can we use 100% can still see? So remember, this point is actually going from 5 to 4 in order to make this conversion. And now what I want to do is that, what if instead of calculating the query vectors directly from the input, remember the input is actually 7,168 dimensions. What if we can just calculate it off this compressed latent query representation? So that's what we're trying to do. So if you remember, this dimension of this is 4, 5 in the previous example. But now, instead of, in this case, we have just as a review. In this case, I'm taking W is here, the whole thing, and then H is here. So we're trying to multiply these two to get my queries. But in this case, instead of W, I like to, instead of H, I like to be CT, I mean this CQ. Sorry, it's kind of messy right now, but I think I want to replace H with C, something smaller. So what I want to do is that I want to rewrite this, delete this, but my first matrix is going to be something smaller. Turns out I only have to use this much. The reason is that in the compressed version, it's much smaller now. Okay, so let's just zoom out a little bit because I want to see that, draw this one more time, this guideline one more time. So in order to make dimension come up, don't do this to me. Doesn't let me draw anymore. All right, okay. Okay, now I can draw again. Great. So now I want to match this 3 dimension here. So I only need to 3 columns of weight in order to accomplish this. And I'm going to use this to just kind of draw this. All right. So what happened here is that I'm going, actually, no, just like this. I'm going down from 5 to 3. All right. So I can use much fewer weights, 60% reduction of weights for my head. And that's what the this latent attention head is able to accomplish. And for key value part, it only need 2. So if I update this, the calculation for my key, okay, so I will only need to select this 2 if my input, instead of from my raw input, I'm going to use the compressed version, which is much smaller. So I can still get this. And then I'm going to just hide this, hide this, hide this, hide this, hide this. And then we can do the same thing for the value as well. So delete this. Now rewrite my matrix modification and to select only the first 2 columns and go way up to select my compressed KV value. All right. Now, if you check all the rest of the multi-head, this head, we did not change anything else other than the fact that we have much fewer ways to train for each head. And you may remember in the earlier I talked about there are 128 heads. So the reduction is quite significant, over 128 heads. They all get reduced in this way. And so another thing that we could later, so I come back, but then you can see that I save some space for you to put something over here. These are the positional embedding using this new technique that came out last year called rotational position encoding. I'm gonna talk about this later, but I'd like to just go to the mutual expert section. Hopefully you can see, follow me up till this point. I still have most of the participants on the Zoom, which I'm pretty happy instead of losing all of you. So I still have most of you still here and also on Zoom. Hopefully this is you're following along. Anyway, so we finish attention, we talk about single head, multi-head, and then adding the latent. And pretty much it's a fancy way of saying you just add one more layer of linear projection in between. But then you have this amazing result of reduction in the number of weights you have to train. For all these red, I shaded the numbers that are in red to indicate that those are the trainable parameters. And in this representation, you can see all the trainable parameters kind of grouped to the left. You can easily visualize everything to the right. It's not being painted in red. You can see that these are all calculated values. They just require memory, but they also are not trainable. They don't need to train them. So this is a pretty neat representation for you to analyze what are the trainable parameters, what are not. Now we're going to talk about matrix of expert. So I'm going to bring back to 100%. So scroll down a little bit to this part. So, and similar than before, I would like to hide something I don't have to talk about right away. Something that's not in the original transformer, which is this router. We're going to hide this little bit to talk about what is in the transformer. the second part, the feed-forward network. So the feed-forward network, so we're gonna start with again 5 dimensions again. This 5, 6 token. So I want to have this process. I could increase this dimension to some higher number, and then could capture a bit more. Like so, for instance, 7 to capture a bit more meaning and logic and ideas, and that's embedded in this neural network. So higher level features, 7, and then do some kind of processing, combination, and bring down back again, similar to what I said earlier. I'd like to bring it back down again so it's compatible with the rest of your stack. Always, if it's nice to have the consistent model size across your stack instead of keep changing them. So we're back to 5. So we need 2 projection, 1 projection to 7, 1 projection to 5, and eventually, and in between, we add an activation function. So this is like the very simple way of explaining how multi-layer perceptron or deep neural net it originally in this manner, kind of feeding it down here with some weights, transform them, activation, transform, linear transform again, and activation. I have some kind of new concept called gate going to talk about that is applying the mixture. But let's see, do a just quick math one more time. Let's suppose I have a feature. Now we're going to look at to the right. So we have 1, 2, 3, 4, 5, 6, and we have another feature on the third row, say 7, 2, 5, 1, 1, 1. Okay. And if we have this weight saying that 0, 1, 0, 1, 0, and that will map to this row and this row, as a result, the final result over here is going to be the combination of these two, the A4, A5, 6, 7. All right. So this is a similar calculation as I did in the attention layer, except that I did it in kind of 90-degree rotation in the more like by rows. I'm combining rows to form new rows. Bring my rainbow. What is happening here, I'm going to do this. Bring different rows and then form a new row and repeat the same process for other rows. And then we zoom out again and can see pretty cool. You can now this is when you can actually see that if you compare the process of this mixture expert of faithful network layer and also the attention layer, and you can see that they are just trying to do combining some data to form new data, except in 2 different directions. In the attention layer, trying to combine column to form new columns, and in the feed-forward network, you're combining rows to form new rows. All right. So that's why in the transformer, you need 2 layers. All of a sudden, you have this powerful result, being able to for machine to learn stuff because you're combining rows and columns at the same time. Whereas in the original neural network, you only combine rows to form new rows. That's it. So now I can combine new rows, I can study to pick out some speed. Now I'm gonna so I like to take the input from the upper layer, which is my attention layer. They become input in my this layer, and I have a whole bunch of weight. In fact, I prepared this one for me to select some random weight. I want to have 7 of this. 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5. That is how much weight I need for this location. So I'm gonna go back to 100%, so easier to see. Okay, I'm gonna copy this weight value. Okay. And then if I would have matrix multiplication, I'll do a linear transform with all these weights, with my input. Okay. All right, so now I have a first transformation. And if you want to add bias to it, suppose there's some bias, I'm gonna divide some few things. -1, -5, -2, like this. Okay. And then so I have this like little trick of adding this 1 here. So if we add this 1 here, I have an extra row augment to this. So all I have to do is if I could expand the measurement multiplication to include this new extra row and column, they will achieve the same purpose of adding the bias. So now adding bias, you can see if I change to 0, the thing starts to increase by one. This is how the bias is being introduced. So I want to just introduce to something like 25 and something like 15. So I have some negative numbers and maybe minus 20 here. Okay. All right. So this is what the first layer of this V4 network can be implemented. And then now I will introduce the activation layer ReLU function. So if I would just take this and just copy them as if I didn't do anything, apply not just like an identity function, it could be exactly the same. But for a ReLU, is basically I want to just eliminate all the negative value and reset it to 0. So that's why I will compute ReLU by hand, find all the negative value, and just to make it 0 and then leave everything else. And so now I'm gonna write the actual code to do ReLU, have a ReLU function built in as well for my example. So I select the entire region of value. So this ReLU, you can see everything that used to be negative with ReLU is 0, which matches the result I did by hand. And now I would like to just apply the same thing again, but in this case, we have 7, 5, and 1. So there's a dimension. And to reverse the process would be 7, 5, 7, 1 to reverse this process. And I go to my random number generator by hand. So this is my random number. I copy this into this location, but I just paste on the value and I can just set some random bias I want, and then repeat the similar process of matrix multiplication. Okay, and then go up to select this one, which is the output from the previous layer, and actually one more time. Okay, and now make sure I select the first extra row here for 1, but I think 1 is missing here. I also deleted this. Okay, add 1 back and remove this. I like this to be neat. Okay. All right. And then do ReLU, which is set everything that's negative to 0. And now I have finished my first before enable first expert. And then if I have a gate, if I put 1, meaning that I would like to multiply 1 to every single value here. So I will select, and then I can do something like this. Select the output and but times my gate, which is per position, 6 location. So that will have just pass through because every single value is 1. If I say I've set this to 0, you can see that it immediately becomes 0. If I set to 0.5, only half of the activation will pass through. And then eventually, I can set to my last layer to just mix it with itself. With only one expert, it's not mixing with anybody else, just a pass through. But what's really interesting is that if we add the next level expert, so I'm gonna do some copy and pasting to my next expert. But before I do that, I only have to modify one place before I make so because for this one, the second matrix I'm multiplying is the input. Following similar logic, we're gonna pass copy to the right. I want to fix the column. In this case, column of V and to AA in order to select, make sure I select this one. As I copy to the right. This is the only thing I have to do before I can copy. Once I have this, then we can just magically somehow copy the entire block of formulas and values. And to my second expert, let's make sure I copy the right offset, which is here, paste, spatial, and value. Voila, I get a second expert. And then I'm gonna do my third expert, do the same thing. Actually, no, not value. Sorry. Come back. I want paste formulas. Okay, and then do one more. So I have 4 expert now. Do formula. Now I have 4 expert easily. And make is it did I paste value by accident? I did. So let me just okay, I just copy this back. That should be fine. This is if I copy this whole array of equation. So I just copy to replace this and delete all this. Let's delete this one by one. Copy again. Sorry. Copy, delete, delete. My second expert is kind of messed up, but okay, now I delete them. I want to copy my formula maybe to the third expert. I can copy the same formula because I share the same formula, same pattern of multi-layer perceptron, and I copy formula, done. All right. They are exactly the same. Again, because I have the same way, but if I just quickly change a few things, then they will be different. Okay, change a few things, just change a few things, but uh, of course, in real application, they will be this will be very different. The idea is that each uh this multi-layer perceptron will just kind of pick up some particular pattern, particular ability, and then you will decide which one you should pass in. So now we're going to do is that suppose I start by every step for expert, and this is kind of tell me which token are being passed through, but using the expert. So suppose this first expert, if this is one, meaning that every single token will use for expert number one. So for expert number two here, say E2. So if I have something like this, it means that the second expert only is applicable to the first and second and third location and so on. So I have this four expert, and then but the gate value kind of just hard code the gate value. In this case, I have maybe use 000, and for last one, I just do this. That's how I would assign the different gate value for each expert. And you can see the first expert is one in all location. Another way to think about it is that every single token would have to use this expert. So the expert number one is a common shared expert among all the different different tokens. Whereas expert two used by half of the token, expert three used by half of the token, and expert four used by 40% of the token, and so on. And then now we could mix them together. So I can write the formula to be this. Select the first one plus select a second one plus. Oops. Oops. All right. This is hard to do. Let me just use my mouse to help me. Select, select my third expert here. Okay. And select my fourth expert output here. It's hard to do. Okay. This is actually doesn't match dimension. Let's just refix this a little bit. Let's let me select. Come on. Go up and change. Okay. Now, so this is how I mix them together. And in the paper that basically you see this F and I and with gate in the coefficient. That's how we just implemented this. Okay. And then last is that I kind of go back to the routing part and to show exactly how instead of I just hard code this gate value can be predicted based on what the input is. So what I'm gonna do is I'm going to go back to 100% and unhide the section that related to routing. So we're gonna unhide this. And the router is that we have this affinity score we want to compute here called affinity score. And so so for sixth position, which expert is most has highest affinity to a particular location. And for this case, I would like to show an example with one shared expert and three routing expert. So that's one of the things that DeepSeek does is that have this like idea of have mixed expert, but it can also have a shared expert. Everybody has it, and routing expert everybody has a subset of this that determined dynamically based on the input. So for the shared expert for affinity score, it's going to be have a sigmoid. Sigmoid is something that will map to 0 and 1. So 1 is the highest probability. For shared expert, we can just hard code this to 1, 1, 1, 1, 1. You always used. And for the other one, it's some kind of score you want to be compute here. So in order to have the prediction, we're going to do another linear projection over here. So then we'll set some kind of weight. And this, I can erase this. I don't need this. This is coming from other examples. Okay, so 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0. And now we'll do a matrix multiplication of this thing and also my input over here to make sure expert model. And I have this one, and it's kind of large. I don't quite like it. But anyway, but I can still map them to sigmoid, and sigmoid is 1 over 1 plus exponent of minus something. I'll select this. And this 1 over 1 the x minus. This is a equation. Now you can see that everything is 1 just because this number I didn't choose carefully. Everything is like super big. And so I would like to make it more reasonable. So how can I do this? I could just purposely add offset, even though in the paper it doesn't add the offset. So I'm going to add the offset to something, say, minus 130. So I'm going to, and this is offset to 60, maybe minus 60. And this is minus 60, okay? So I'm going to just update this function to add this offset using the trick I just talked about earlier, that update this to add this offset. So I can have something more in the range with a sigmoid function. What's interesting would be anything between zeros, kind of like ballpark between -3 and 3. So you can see statistic distribution of between 0 and 1. Otherwise, it's too big, it's always 1, or too small, it's always 0. Too small is always 0. It's not interesting. So I use this bias to purposely bring this predicted value down to a range that's be interesting. So once I have this affinity score, these are predicted. So I can sort them by affinity score, or if I want to sort them, store each one, sort by each column, sort them. Okay, and then ascending, descending, -1 descending, and I have this. I forgot to put 1 into the actual here. This one, I hard-coded 1 and copy all the sort. So you could see in this case, this is still super big. I don't know why here. Something wrong here. But anyway, so 0, 0 is it means like it seems like this X is not nobody. Second token is not selecting any expert. It's only going to be used the first expert here. So what I want to do now is to pick only the top 3 here. So the number 3 is here. This is rank 3 after I sorted it. So if I would go back to take my affinity score and check that if my affinity score greater, one more time, if my affinity score is this block is greater or equal my third position. If so, I use the same affinity score. If not, it's 0. So this is the logic here. Then you can study to see that now I only pick top 3. Every single column is only selecting 3 expert. Every single column is 1 position. Every position select only 3 expert. 1 share across, and 2 selected out of the other 2. So once we have that, I could replace my hard-coded get value with the rule I have here. So using references, I just equal here, come on, equal something. I select this. Okay, now I just select the value equal here. Now I delete this first. I think I'm almost done to implement DeepSeek. It's a bit more ambitious than I thought. I thought I can do it within an hour, but it's just not possible, it turns out. Maybe I talk too much. Maybe do I explain too much? That's why I couldn't finish. select second row, and that's one is 11111. I can just hard code it. I don't have to copy anymore. And now you can see that is being weighted differently, and it's being set to 0 because the second expert not applicable to our second and sixth positions. Okay, so that's what I have here up to this point. Hopefully you appreciate the way that I explained how the feed-forward network is can be calculated and over multiple experts and can mix them together with a router. That's how what DeepSeek does. And once I have this set up, and I'm going to zoom out a little bit and show something kind of fun with Excel that what you can do is that you could go to formula and do this trace precedent. You can start to see that, hey, this mixture actually mixing the output. That's not, let's just do zoom level to 25. You can see it more clearly. And you can trace the calculation back, this trace over here, and then do this and do more. Can just kind of keep going back. You can see that flowing how the data is can be back propagated all the way back. And depending on this concatenation of three attention weight output, and this come from this matrix here, similarity matrix, and going all the way up and going to this go to the latent Q and key and eventually trace back to your input. That's all this in the opposite direction. And you can also do this in the forward direction as well. So they removed all the arrows. Okay, so this is like a major innovation that is, as you can see in the DeepSeek. Hopefully, I think, in my opinion, I guess that a lot of this new ability to be able to train very quickly came from the fact that there's a huge reduction in the number of trainable weights in the multi-layer, multi-head attention. You can visualize here, there's actually quite a reduction while being able to preserve the learnability from the data. And another thing I think actually play a role is the way that you're able to bring this positional encoding a lot closer to the attention head. So you can see that attention key is over here being appended to your matrix. Or do this extension, you don't have to change everything else. You can see that if your query and key vector grow in this way, it doesn't change the layout of your multi-layer, multi-head attention scale dot product. And that if you have seen the transformer paper, the original positional encoding is actually outside of your encoder block and it was being applied to the input right in the beginning. But where in this case is inside the attention block, meaning that this block that can produce these two things, but this happened at every single layer. Could have how many layers? They have something like 67 layers, something like that. There's a lot of layers. You have 67 chances to introduce rotational encoding in this way. Whereas original positional encoding only get introduced one time, and you are hoping that you can pass down the stack, but sometimes you start to lose information about position. Okay, so I guess today I'm not gonna have time to break down the rope since it is probably required. It's not specifically about DeepSeek. It's just a way that a lot of newer model these days, architecture, they use rotational position encoding. I do have exercises I'll share in some other method, in other manner for you to get into rope if you want to, but not today. So I hope that I kept the promise of going through DeepSeek, focusing on two most important architectural component, which is the multi-head data intention and also the mutual expert being able to use shared and routing expert in the same architecture. Okay, so well, it took me 70 minutes to go through all this, and I hope that you learned something from me today. And so I probably don't have time to take questions since it's already getting pretty long over time for today's lecture. But Anna, myself, Milton, Nolan, and different our TAs, we're trying to get back to the question. We get tons of questions from online, also from our webinar. Zoom webinar. And thank you so much for listening. And so we'll try to follow up by sharing this my sketch after we clean out a little bit. But then also I would like to use this opportunity to challenge you to watch a recording and see whether you can replicate this Excel sheet. I might share this a little bit later so you could have time to try to watch the video. And I actually have 3 copies of our deep learning math workbook as the prizes. If you somehow manage to reproduce my calculation today, if you email me, first 3 that managed to do that, I would like to give you a copy of this new the deep learning math. You have 300 puzzles you can solve to really get a strong foundation understanding of deep learning math. Okay, so this is all I have, and thank you so much for listening. And well, I should bring my camera back. You can see me and say a proper goodbye. All right, thank you for listening. I'll see you next time.